Modern operating systems are pretty complex, as anyone who's here probably knows, if you've done any development. And there's a lot of things going on. Billions of instructions executed per second, and millions of events that are of interest going on. And often you need to be able to find out at a low level what's happening. One or two bad things, or a pattern of bad things happening in those millions of instructions. So Zen Trace has been a tool that I've found very useful over the last several years during my, while doing performance analysis and debugging, for gathering a huge amount of in-depth information about what the hypervisor is doing, and what guests are doing and how the hypervisor is responding to that. So part of the problem, though, is that there's too much information. So in order to be able to process that information and gain some meaning out of the chaos, I developed a tool called Zenalize. So my goal for this talk, well, my big goal is pretty simple, okay? There are people in this audience for whom Zenalize would be a useful tool for them, especially developers, but also some end users. So I want them, the people for whom it would be useful, to use it. That's the big goal for my talk. And as a subsidiary goal to achieve that end goal, I want everyone here to leave with a basic understanding of what Zenalize does and what it's useful for. Okay, so to accomplish those goals, I'm going to talk about, I'm going to give an overview of Zen tracing. I'm going to talk a little bit about when Zen Trace is useful as opposed to some other debugging or analysis tools. I'm going to talk about the core functionality of Zenalize, the key problems that it was designed to solve. And then I'm going to talk about Zenalize as a platform for doing new kinds of analysis. And then finally, I'm going to give a couple of example case studies to give you an idea how I've been able to use it to do performance analysis and debugging over the last several years. Okay, so the Zen tracing mechanism, at a minimal, a trace record is a minimum a 4-byte event number. These are trace events are generated at different points during the code by calling a function. And the trace record can also contain a TSC timestamp of when the trace was generated, and also an optional trace-specific data of a variable size up to 28 bytes. There's an event mask, which is used to control which events are logged, so you can turn on and turn off events at a certain granularity. When events are generated, they're put into per CPU trace buffers inside of Zen. So each CPU has its own buffer to avoid having to deal with locking issues. Then the buffers are read by a process in DOM0 called Zen Trace and copied to disk. So the key attributes about Zen tracing is that you get lots of detailed data about stuff that happens inside of Zen. There's a moderate amount of CPU and disk overhead. CPU overhead because there's copying involved, and disk overhead because you're writing to disk. And the data in the trace buffers is not persistent on a host crash. So it's useful for debugging guest crashes or anything in the host which, doesn't crash it. But if it crashes, then printk may be a better option. So it's particularly useful if you need to understand both macro and micro effects. If you need to be able to look and say, at a high level, what's going on here, what activity is taking a large amount of time, and then be able to dig down deep and see one specific interaction, a sequence of events, as opposed to an aggregate. So, and I've used this for performance analysis, debugging. Sometimes you have a million interactions that happen in a second, and one of them is bad, right? So you need to have the million of them and then be able to search down and find out the one that is causing the problem, as well as understanding guest behavior. So there's some other really common techniques that we have in our tool bag, and the most simple one for kernel developers is printk, right? So printk is useful for things that don't happen very often, and it's key if the host may crash as a result of something that's going on. But it's not very good for if there's a million things that happen in a second, because it's too slow. Xenoprof is another tool which is useful for analyzing guest behavior, where the guest is spending its time, but it's statistical. So it'll give you a big aggregate amount of information, but it only gives you basically probabilistically a percentage-wise of where the guest has spent its time. So if you need concrete data about what a sequence of events, then Zen Trace is better. And there's also Zen performance counters, which will give you an exact number of something that happened or hasn't happened. But again, it's an aggregate number as opposed to a sequence of events. Okay, so in order to understand Zenalize, I'm going to cover these two key types of trace events that that it can particularly draw a lot of information from. The first is tracing run state changes. So a run state change happens whenever a vCPU changes from blocked to runnable. That means it wakes up. Or if it becomes scheduled, it goes from runnable to running. If it's preempted, it goes from running to runnable. And if it blocks, it goes from running to blocked. So this allows it to figure out which vCPU is running on which physical CPU. It also allows it to analyze how much time is spent in the different states, blocked, preempted, waiting for the CPU after being woken up, and so on. The other key trace are traces that happen on VM exit and VM enter. And the thing about these is that on the VM exit and on the VM enter, you take a trace and you take the TSC. And what this allows you to do is to determine how much time was spent inside of Zen for a particular VM exit. So it allows you to sort out how much time and for what reason you're spending time inside of Zen so that you can optimize that. Okay, so here's the core functionality of Zenalize. The first major problem that you run into if you're going to look at Zen traces is that the Zen trace file doesn't have the traces in order. What happens is, suppose that there's an interaction and that's because the trace buffers are on a per CPU basis. So imagine that there's an interaction that you need to understand that covers 3 CPUs. It goes A, B, C, D, E, okay, on 3 different CPUs. When those go into the trace buffers, each trace buffer will have a bunch of things in it beforehand, and then that record will be put in, and then a bunch of things will be put in afterwards. And eventually, sometime later, the Zen trace daemon will read this whole buffer with the thing right here, right in the middle, write it to disk, this whole buffer with the thing here and here in the middle, write it to disk. And so what you get is the interaction you need to see is spread out in the file, maybe up to megabytes apart. So what Zenalize does is it attempts to process the records in the order that they were originally generated. And it's actually a very complicated process. Basically, it uses the TSC values, but because TSC values, there's a certain amount of skew, it attempts to detect skew by looking at the run state changes. So I won't get into detail about that, but that's one of the things that it does. The other thing that it does, the problem is of mapping small things to large things. So you can look through the file, and even if things are in order, you can say, okay, the guest did this and this and this and this, and this exit here took, 11,000 cycles. But 11,000 cycles is like a few nanoseconds. Is this a problem overall? How do we find broad trends? So Zenalize has functions to aggregate information so you can see larger trends. It will see how much time total it spent doing things. It will do averages. It will also do percentiles, 5th, 50th, and 95th percentiles. The final thing is the final key of the functionality is that the data in the trace file is per CPU. But what we care about is actually what's happening on a vCPU level. And the vCPU may move across physical CPUs. So the Zenalize uses the run state change traces to track vCPUs across physical CPUs, and it aggregates the data on a vCPU level, even as it moves across physical CPUs. So here's I'm going to give you a couple example outputs. Here we have, this is the dump mode. In dump mode, you have one line per trace record. Okay. On the left here, we have the time offset since the beginning of the trace file. And the next kind of column over here with the X's and the dashes indicate which physical CPU this trace record happened on. So the X indicates the CPU. So the first one happened on physical CPU 1, the next 2 on physical CPU 0, the next 3 on physical CPU 1, and so on. The next column over is the currently executing vCPU. Okay, so you can see that we're running both, domain 4 is running, virtual CPU 0 and virtual CPU 1. And the next thing over is a human-readable interpretation of what the trace is going to be. So we can see we have VM exits, we have fast MMIO, and there's information about what the exit reason was, the instruction address at which the VM exit happened, the virtual address that the MMIO happened, and so on. So there's a lot of extra data in there that if you understand what Zen is doing there, you can dig out. Okay, the next mode is the summary mode, where it runs through the whole file and gives you an aggregate information about everything that happened in there. So in general, for HVM domains, we have the exit reasons broken down. And so we have the first exit reason is the exception NMI. And as you can see, it's kind of a standard output. The first thing is the count. So there were about 5.7 million exception VM exits in this trace. The next is the total amount of time due to those VM exits. So this is about a 30-second trace. And of those 30 seconds, 10 seconds was VM exits due to exception or NMI VM exits. And then a percentage of the overall time, about 35%. Then we have average. So the average exit time was only 4,000 cycles. And then we have percentiles, 5th percentile, 50th percentile, and 95th percentile. So in this case, it's a pretty tight thing. And then underneath of that, we have more. We have it broken down into more specifics. So there's lots of reasons why you might take an exception VM exit. If you may be propagating a page fault to the guest, maybe doing fast MMIO, you may be doing different kinds of fix-up or shadow page table operations. And you can see in this case the fast MMIO has the lion's share of it. Almost all of that happens due to fast MMIO. So I'm going to talk about what we'll see later, why that's using so much time in there. Okay, here's just another example output. Other ways of doing things. You can set it to every 10th of a second output information about what's going on. So this is time that domain 4 is spending in each of these in VM exits for each of these different reasons. So we have the one on the bottom is running, and the next one up is MIO. So you can see that over time, it's spending a lot of time running, but it's also spending a huge amount of time in MIO. And the thing here in the missing part in the middle is because there were actual lost records. Sometimes the disk bandwidth isn't fast enough to write stuff as fast as the trace records are generated, and then it just loses records. And other random, outputs are, so this is a scatter plot of x-axis of time, and the y-axis is the EIP at which the host time interrupted the guest. So this is sort of a visual representation of how the guest is actually running and where it's spending its time. Not particularly interesting in this case, but there are cases where things like that are useful. Okay, so there are lots of other advanced features that go in there. There's enumeration of different kinds of addresses, so that if it can tell you MMIO or IO or VM exit addresses or emulation addresses, it will add them all up and say that, well, you did 1,000 MMIOs at this address and 200 MMIOs at this address, and so on. You have the ability to have symbol file translation. So if you can get the symbols out of Windows, then you can pass that file into Zenalize, and it will tell you we did a VM exit here, and this is the Windows symbol that corresponds to this VM exit. So it's useful in kind of figuring out what the guest is trying to do. The linear page table back calculation, Windows uses what's called a linear page table, which is a neat trick so that if you're given a virtual address, you can do a simple calculation to find the virtual address of the PTE corresponding to that virtual address. Does that make sense? So if I want to modify something about this virtual address, I can do a simple calculation and find right where the PTE is in kernel memory. Well, we can also do that backwards. Given this area in kernel memory, we can say the virtual address that corresponds to this PTE is this. And that can be really useful as you're correlating, say, propagation faults or other things like that to updates that you're seeing in the page tables. Yeah, so there's many more advanced features that I've just added in as I've needed them over the years. So the key thing about Zenalize is that it's useful as a tool, but I find it more useful as a way to add more analysis, right? So it's probable that Zenalize may not be able to answer the exact question you have right now, but it's a great platform to modify to be able to add questions that you wish to ask of data, because it's already done a lot of the hard work for you. All the hard work of processing things in order, of dealing with lost records and so on is already done. And there's a big library of statistical things like that. So it's more a tool to be developed and modified than to just take as it is and use. Okay, so here we have a couple of case studies. So this is about WinXP and the TPR, the Task Priority Register. So you may remember we took this trace and we saw that it's spending 33% of its time, in this case, running inside of Zen, doing the exception handling. And almost the entirety of that can be attributed to fast MMIO. So why is it spending 33% of its time doing MMIO? So we looked at the MMIO enumeration, and these are all of the MMIO addresses. And we find that half of them, actually basically all of them, are either reads or writes to this physical address. And that turns out to be the TPR register. The TPR register is on the, I get confused between APIC and ACPI. It must be an APIC, yeah. That controls the interrupt level and which things can interrupt other things. And in Windows XP and earlier, Windows writes to this extremely gratuitously. And it's not that expensive as an MMIO, but as a VM exit, it actually costs a lot. So the solution here, in more modern versions of Windows that actually do what's called lazy TPR, which means that they only update the TPR when they need to, and it greatly reduces the amount of time spent in the hypervisor. And so what we did as Citrix was we basically binary patched Windows XP so that when you install the PV tools, then it binary patches the TPR thing, so it does lazy TPR and avoid the vast majority of these exits. Okay, and there's another quick example how I came up with some of the shadow performance optimizations. So I should emphasize that these numbers are actually doctored because I didn't have time to run actual numbers with shadow off and with the out of sync feature on and off. So now we fixed the TPR and we're running another test, and we're finally spending about 15% of our time in exceptions still. But this time, we're actually spending about 13% of our time doing emulation. So, and not just any kind of emulation, but in the linear map, modifying L1s. So, and then if you go down to the dump mode, where you're looking at a specific things that Windows is doing, you'll find that we'll have this sequence a lot. Windows will take a page fault, and then it will write to the PTE, but it will write a transition PTE as it's paging something in. And then it will finally write the real PTE and then access it. So what this looks like in the old version, Shadow 2, is you have a page, you go into Zen for the propagate, okay, and then you emulate the transition PTE, and then you emulate the real PTE, and then when you access it, you just have a TLB mess because the shadow is already there. What we can do instead with out of sync is that we mark the page out of sync ahead of time, and in that case, the exit looks to look like this. You still have the propagate, but then when Windows writes the transistor PTE, it's just a memory write. It doesn't go into Zen at all. And then when it writes the real PTE, it's again just a memory write, so it doesn't go into Zen. And then when the guest actually accesses the page, because the shadows haven't been updated yet, it causes a page fall at that point. And then we will propagate the PTE change. And the key thing here is that not only are we doing one fewer VM exit instead of two, but that VM exit itself is shorter because you're not having to do a lot of the emulation, instruction decoding, and so on. Another example, there's other examples, but that I could go into how. But the key is that being able to look at what the operating system is doing at a line-by-line level, being able to look at what was a problem at a larger level allowed me to decide what to look at a line-by-line level. And being able to look at the line-by-line level allowed me to make these kinds of optimizations for Shadow 3. Okay, so I've given you an overview of Zen tracing. I've talked about when Zen trace is useful. I've talked about the core functionality of Zenalize, using Zenalize as a platform to do new analysis. And I've given a couple case studies that I've used Zenalize for to do analysis. So hopefully, those of you here for whom Zenalize will be useful, you will use it now. And everyone has a basic understanding of what Zenalize does and when it actually is useful. So it's available online. It's open source on ZenBits. And with that, I will take any questions. Recreate, say again? Mm-hmm. It's not, at this point, there's a TSC drift issue. So generally speaking, you can discover the causal order between things, especially if the causal order involves a run state, a vCPU moving from one place to another, because you can tell which orders are valid or which orders are invalid. But at this point, because we don't have a global clock and the TSCs aren't 100% accurate, you can't rely on the TSCs for sure to say, I know for a fact this happened before that a lot of times. But it is still useful. You can tell, you can kind of look at it and say, well, this order doesn't make any sense. But if it happened in this order, then it would make sense. There's, in the Zenalize directory, there is a self-modifying HTML file which has some information about it. Unfortunately, it's very sparse. It's hard to make time to actually do a lot of writing when there's so many actual things to analyze. As an API, I'm not sure what you mean. Yeah. Uh-huh. I wouldn't rely on Zen Trace not changing. Yeah, I think it's designed to be fairly fluid. So I wouldn't. So you're welcome to steal code out of it if you wish to make it your own. Or a wrapper or something like that. Yeah, but I certainly plan on, as I do updates, changing everything. It's definitely a developer tool. It's meant to change and not be part of a. It's not meant at this point to be part of a component. Yeah, Jeremy.
Could you consume those events in a streaming way rather than saving them out to disk and sort of do processing on the fly?
Yes, you can. There's in fact a thing called ZenMon, which was meant to actually, it uses the Zen tracing mechanism. It will map the Zen buffers and it kind of analyze stuff. But it's really been bit rotting. I don't think anybody's done anything with it for several years. So I have thought about, it's a bit challenging to do that, to structure it so that you can actually stream stuff out. And the other thing is that often what you want to do is you want to look at the data and then have another question you want to ask. So you modify Zenalize and go back and run it again. So this iterative thing is pretty useful.
So it's sort of similar to the UBC thing, whose name I've forgotten. That's fine. The other question, though, or observation, was that it's very similar to the event tracing stuff that's in Linux that's grown up over the last year or so. How practical would it be to have something in the kernel read the Zen trace buffer and then integrate that with the Linux event stuff so that you can sort of see a unified Linux events mixed with Zen events?
I don't know. That's an interesting idea. Yeah, I haven't looked closely at the Linux tracing event stuff. I've been a bit jealous of the number of people that have to actually do development of.
Well, that's kind of what I was thinking of, is that if you can sort of hook into that, then
yeah. That's an interesting idea. I'll look into that. So, Stephen? Yeah, I haven't done. It's been years since I've done an actual performance comparison, but I think it's probably between 10 and 20%. It obviously depends on how much you're using the disk and how many things are generated. So if you're running SpecGBB, which doesn't do any interaction with Zen hardly at all, then there's almost no overhead. But if you're doing a kernel build, which does a huge amount of page table updates and stuff, which obviously works with Zen, then it's a much larger overhead. Okay. Any other questions?
One more question. Like in some kind of common case, how much data will Zen Trace generate per second?
Yeah. So if you have a really heavy workload, if you're doing performance, often you're doing a Zen trace because there's a huge amount of data. Like a 30-second trace will be like maybe between 300 and 600 megabytes. So gives you an idea.
Thank you.